Hello, everyone. I'm Manos, and I'm going to present QoS, Quantum Operating System. This is a joint work with my collaborators, Francisco Romão and Nathaniel Tornow, and my advisor, Pramod Bhatotia, from the Technical University of Munich. We are heading towards an exciting quantum computing era, where quantum computing promises exponential speedup in certain computationally hard problems, with many applications, for example, quantum chemistry, machine learning, cryptography, and material science. At the same time, there is widespread adoption from the industry from all major tech and cloud providers. Quantum computers are a reality. Our journey begins from 2023 with the IBM Falcon and Continuum H2 processors, and we evaluate QoS on the real IBM Falcon processor. Recently, we saw breakthroughs such as the Google Willow processor, and we have a quantum cloud with hundreds of thousands of users and billions of executions. In the near-term future, we expect even more advanced capabilities, such as distributed quantum architectures. However, these quantum architectures are managed in an ad hoc manner, since there exists no operating system support to manage them. So the question is how to manage quantum computers. In the classical cloud, we know that we have Mesos, Kubernetes, and other systems. In the quantum cloud, can we use or adapt these existing cloud operating systems for the quantum computers? Unfortunately, the answer is no, because quantum computers are fundamentally different compared to classical computers. To understand why, let us first explain how quantum computers are programmed and used. So quantum programs are represented as quantum circuits that consist of qubits, which we initialize to 0, as we do with classical registers. To change these qubit states, we apply unary gates that act on a single qubit, or binary gates that act on 2 qubits. During quantum execution, the quantum state is a superposition of both 0 and 1 at the same time. So to get a final deterministic outcome of 0 or 1, we need to measure the qubits. Quantum circuits are characterized by 2 properties. The first is the number of qubits, which is the width, and the second is the number of consecutive gates, or depth. Also, in this representation, time flows from left to right. Using this quantum circuit abstraction, let us explain to you how a quantum application works. Say that we have a graph that we want to perform the maximum cut problem on it, which is a well-known and hard problem. We encode the graph and the problem as a quantum circuit automatically, and we execute this on a quantum processing unit, or QPU for short. Because of the non-deterministic nature of quantum processing units, we have to run this thousands of times, and the result is the probability distribution of bit strings. In this problem, the highest probability bit string also represents the solution to the max cut problem. Now, let's go one level deeper into quantum circuit execution. QPUs have a physical layout with physical qubits that are connected with links. So we must be able to physically map the circuit on the qubits. It must be able to fit inside. Also, the binary gates require a physical connection between the 2 qubits that it acts on. This mapping and execution itself presents 4 unique challenges compared to classical computers. Let's start with fidelity. Unfortunately, current QPUs are susceptible to noise errors, and every circuit operation adds more noise errors to the execution. This means that the execution results eventually are noisy. So on the right side, after execution, this probability distribution doesn't have anymore a single distinct highest probability anymore. To verify this also experimentally, we plot fidelity, which measures the quality of the quantum computation. It is a state-of-the-art, it's the standard metric in quantum computing, and we're going to use this presentation a lot. And higher is better. On the x-axis, we increase the circuit width, the number of qubits, so the application size. And we can see that there is almost a 99% drop in fidelity for large circuits. The problem is that large circuits suffer from low execution fidelity. However, we optimize the circuits to be smaller in width and depth, which leads to better fidelity. The second challenge is utilization. On one hand, large circuits have low fidelity, as we just saw, but on the other hand, small circuits have low utilization. In this case, we allocate 3 out of the 7 physical qubits of this QPU, so we have only 42% utilization. As a side note, circuits cannot be preempted during execution like we do in classical computing. Again, to show this experimentally, we plot utilization, where of course higher is better. And on the x-axis, we increase fidelity. And ideally, we want a fidelity of 1. If we do this, unfortunately, we have less than 30% utilization on this specific QPU. So the problem is that solo circuit execution has to sacrifice either fidelity or QPU utilization. However, we multi-program small circuits on a QPU to increase utilization. Next, we have heterogeneity. QPU qubits have different error rates, as you can see on this picture. Also, the physical links themselves also have different error rates. Even worse, QPUs of the exact same model, IBM Falcon in this case, have different error rates. And to put the cherry on the top, QPU error rates change over time as well. In this plot, we have fidelity where higher is better, and we have 4 different dates in November 2023. 2 IBM QPUs of the same model, Perth and Lagos. And we can see that while on one day Lagos underperformed compared to Perth, the very next day it has higher performance. So the problem is that QPU fidelity varies across space and time. However, we can estimate this execution fidelity a priori without really executing the circuit. Finally, we have load imbalance. We just saw that QPUs are vastly heterogeneous, and users ideally want high fidelity. But cloud providers also want high resource efficiency. This leads to a tension between those two. And here we plot the number of pending jobs for these IBM QPUs, where equal is better because it means load balance. These IBM QPUs are of the same model, for fairness, and we can see that Cairo, compared to Hanoi, has almost 60 times lower load. So the problem is that there is an inherent trade-off between high fidelity and high resource efficiency. However, we schedule circuits in a way that optimize both fidelity and resource efficiency. To sum up, QPUs suffer from low utilization, low fidelity, spatiotemporal heterogeneity, and vast load imbalance. While there exist some ad hoc approaches for these problems individually, we ask the following question: how to design a unified operating system that manages heterogeneous QPUs with high fidelity and high resource efficiency? To this end, we propose QoS, Quantum Operating System, which is the first unified system stack for managing QPUs while mitigating their inherent limitations holistically. The core contributions are that we achieve high fidelity and high resource efficiency. We systematically manage the trade-offs associated with quantum cloud computing, and we achieve intra- and cross-stack optimizations. Hopefully, I have motivated the need for QoS by now, so let's take a look into the system design. At a high level, users want to execute their quantum circuits on QPUs and get their execution results. QoS comprises 2 high-level components. The first is the QoS compiler that optimizes circuits to increase execution fidelity. And the second is the QoS runtime that multiplexes circuits across space and time to increase the resource efficiency. So these are the 2 high-level goals. Since QoS comprises diverse mechanisms, we need a glue that holds them together, which is the kernel abstraction that acts as a common denominator across these diverse mechanisms. Let's go one level deeper and see the workflow at the same time. We said that users submit their quantum circuits to the compiler, which optimizes them and outputs kernels. The QoS runtime comprises 3 internal components inside. And the first is the estimator that, of course, estimates the fidelity performance a priori. The second is a multiprogrammer that bundles kernels to increase QPU utilization. And the third is a scheduler that schedules these bundles to balance fidelity and QPU load. After execution, the multiprogrammer fetches those bundle results and separates them and returns them to the users. In this talk, I will focus on the compiler, multiprogrammer, and scheduler. The compiler answers the following question: how to increase the execution fidelity on noisy QPUs. We compose complementary optimization techniques in a single compilation pipeline, but the challenge is how to compose techniques that work on different abstractions, which is a common theme in quantum computing. Our approach is an LLVM-like design with an intermediate representation, analysis, and transformation passes. Our frontend takes a possibly large circuit and performs analysis passes that create the IR and some properties. The middle end iteratively optimizes this IR and updates the properties accordingly. And the backend outputs the final optimized kernel with the final updated properties. Specifically in the middle end, the challenge is which optimization techniques to apply and in what order. And our approach involves identifying hotspot operations that impact fidelity the most, because not all operations affect the fidelity the same. We deploy a greedy algorithm that applies these techniques in the order of hotspot elimination efficiency. So starting with a direct acyclic graph IR and some hotspot analysis from the previous analysis passes, we apply one or more optimization passes that iteratively optimize this IR and minimize the hotspots. For more details, you can check the paper. Let's see the multiprogrammer. The question is simple: how to increase QPU utilization? We bundle multiple kernels on the same QPU, but unfortunately, there are two main challenges. The first is temporal utilization. Let's say that we have the red and the green kernels, and we allocate them on this physical layout. But we notice that the green kernel has a longer runtime. This means that during the green execution time, the red qubits will be idle, which underutilizes the QPU. The second challenge is destructive interference due to collocation. There's a specific type of noise called crosstalk noise in quantum computing, and it affects physically close gates that run in parallel. So in this case, if these two gates run on physically close links on the QPU, there is a high chance of crosstalk noise destroying fidelity. To address both challenges, we use a compatibility score and a buffer zone. The first component of the compatibility score is effective utilization, which captures the temporal utilization as well. So in this case, these two kernels have similar runtimes. The compatibility score also quantifies crosstalk, and if it passes a certain threshold, we are good to go to collocate these two kernels. When allocating these kernels on the QPU, we leave some empty qubits as a buffer zone to mitigate crosstalk. Finally, let's see the scheduler. The question is how to balance QPU load, and of course, we want to evenly distribute kernels across QPUs. The problem is that there is a fidelity load balance trade-off that is stemming from the QPU heterogeneity that we mentioned. Our approach involves multi-objective optimization, where the criteria are fidelity, load balance, or both. On the right-hand side, let's say that we have this circuit that we can execute on the blue or the red QPU. Also, let's say, for the sake of this example, that on the red QPU, we have 3% lower fidelity, but 4 times lower waiting times. These seconds are the queue of the QPU. Our scheduler can make the conscious decision of scheduling the kernel on the red QPU, sacrificing 3% fidelity for 4 times lower waiting times. Now, let's see how we evaluated QoS. We implement QoS in Python based on the state-of-the-art Qiskit quantum SDK, and we answered 2 main research questions. You can find many more results in the paper. The first question is, what is the compiler's impact on fidelity? And the second is, what is the multiprogrammer's impact on fidelity while increasing utilization? Our methodology involves real IBM QPUs and a classical server, state-of-the-art quantum applications and benchmarks. The baseline is the Qiskit compiler that we mentioned, and a state-of-the-art baseline for the compiler and a state-of-the-art baseline for the multiprogrammer. We evaluate fidelity where higher is better and utilization which is also higher is better. Let's see the compiler's performance. As I have said many times, fidelity higher is better. And we evaluate 3 benchmarks in this case. And on the x-axis, we increase the circuit width or the application size. The blue bar is Qiskit, the orange bar is the baseline, and QoS is the green bar. QoS achieves 2.5 times higher fidelity compared to CAT-QC, the baseline, and almost more than 400 times higher fidelity compared to Qiskit. Let's see the multiprogrammer's performance. Again, we plot fidelity, where higher is better, and on the x-axis, we increase the QPU utilization. The blue bar is solo circuit execution, no multiprogramming. The orange bar is the baseline multiprogramming approach, and the green bar is QoS. QoS achieves almost 10 times higher fidelity compared to solo execution for the same utilization, and 15% higher fidelity compared to the baseline for the same utilization. To conclude, quantum computers face unique challenges: low fidelity, low utilization, vast heterogeneity, and vast load imbalance. We propose QoS, quantum operating system, that improves fidelity with complementary compilation passes and improves resource efficiency with multiprogramming and scheduling. You can check our code on the GitHub link below, and thank you. I'm waiting for your questions.